are watching session number 2 of the chapter Some Basic Concepts of Chemistry. In the previous session, we discussed about matter, the classifications of matter, properties of matter, physical quantities and scientific notation. In this class, we'll discuss some other basic concepts related to matter. Now, I am going to talk about what actually accuracy stands for, what actually precision stands for. Accuracy and precision I am going to discuss now. So, we'll conduct one activity and based on that, we'll try to define what actually accuracy and precision stands for. Let us assume I have 3 students and I name them as A, B, C. 3 students I have. So what I am going to do is, I will give you one chemical compound, the same chemical compound to all the students A, B, C. I inform them to calculate the weight of the chemical compound what I have given using some kind of balance, maybe physical balance or digital balance, and I insist them to take 2 readings, 2 records. I insisted. So they are going to perform the experiment and they are going to hand over me the readings or the records what they have observed. So let us assume student A gets the reading as 1.95 and 1.93 in terms of grams you can consider. Whereas students B is going to get 1.94 and 2.05. Student C is going to get 2.0 and 1.99. So these are the different 2 readings with respect to student A, B, C. But actually the actual weight or actual measurement of the given substance, that will be 2.00. So the observation or the reading, and that we call it as a true value. Okay, and without error, and if you calculate the particular value with the true value, and let us assume the true value of the given compound will be 2.00. okay, and but what happens, while conducting experiment in lab, some personal error or some instrumental error takes place. Because of that, the students won't get exactly 2.00. Some maybe get less than 2.0 or greater than 2.0, and that we call it as errors. And due to the presence of errors, the students are going to get such kind of the different readings here. Okay, and now we'll see which students is going to get more correct, which is more accurate, which is more precise, we'll see now. Okay, so now keep in your mind the true value is 2.0. Fix that the exact or the true value is 2.0. So now we'll see student A, what kind of readings he got. Actual true value is 2.00. Student A, the first time here he is going to get 1.95. Second time he is going to get 1.93. Okay, so now the true value is 2.0 and he got 1.95 and 1.93, and now one can easily guess that 1.95 and 1.93 is far away from the 2. Okay, so what I am going to say is student A, and he is not going to get the accurate reading. There is no accuracy, I can say here. Why there is no accuracy? Because when compared with the true value, this 1.95 and 1.93, we call it as particular value. There is the large difference we are going to observe. Therefore student A is not going to get the accurate or accuracy. Okay, and now he is going to get the 2 readings as 1.95 and 1.93. So these 2 readings, of course they are not near or equal to the true value, but these 2 are almost nearer to each other. Okay, so 1.95 and 1.93. So what I am going to say here is student A, okay, and he is going to get the precise reading. Okay, so he is going to get the precise reading. So in short, I can say, if you compare the true value, if you have one particular value and you are going to compare the particular value with the true value, and if it is almost equal, and we can say it as accuracy. If it is not almost equal, it is far away, and we call it as no accuracy. Okay, and if you consider the particular values only, the measurmental values, okay, two different readings we have, and of course they are not nearer to the true value, but these two are nearer to each other, and that we call it as a precision or precise reading we are going to see here. So now this is accuracy and this is precision. So now you just see the statement what I have written, and later we'll see what happens in case of student B and C. So accuracy is agreement of a particular value to the true value of the result. So which is the true value? 2 is the true value. Which is the particular value? 1.95 is the particular value, and 1.93 is the particular value, and you need to compare the particular value and true value. If they are almost nearer to each other, and then we are going to say that result or that reading is accurate, otherwise no accuracy we are going to see. In case of precision, closeness of various measurements for the same quantity. See here, closeness of various measurements here. We are not comparing with the true value. Remember, in case of finding precision, we are not supposed to compare with the true value. We are supposed to get the particular value only, and how many various measurements we have, and we are going to observe here. So 1.95, 1.93, these two are two different various measurements, and they are almost close. So closeness of various measurements for the same quantity. So student A calculated 1.95 for the given compound, and for the same compound he is going to get 1.93 only because of error I told you, and that we call it as what actually the precision here. That is the main difference between accuracy and precision. So try to know, if you want to see whether the observation or the recording what we are going to get, whether that is accuracy or not, or we have precise reading or not, you have to see the readings as well as the true value. If you want to see the accuracy of that one, compare the particular value and the true value. If they are equal or almost equal, then you are supposed to say that has attained the accuracy. If that is far away, then no accuracy we can say. In the case of precision, you should not compare with the true value. The two different measurements, or how many measurements we are going to see, we are going to link with each other only. If they are almost near to each other, or closeness in the measurements you are going to see, and that we call it as what actually precision here, accuracy and precision. So now what I am going to say here is student A has no accuracy, whereas student A has a precision. So the results or the reading what student A got, that has a precision but not accuracy. So I am going to write here student A. Okay, so the readings are precise. Okay, readings are precise but not accurate. See here, student A, the results are precise but not accurate. And how I said they are precise? Because the two readings are almost nearer to each other, therefore I said the precise. And why I have written not accurate? Because when you compare the particular value with the true value, they are far away or not nearer equal to each other, therefore not accurate I am going to see. So now we'll see what happens in case of student B. Okay, see here. First we'll see what about the accuracy, and later we'll see what about the precision. Accuracy means you have to compare with the true value, isn't it? So the true value is 2.00. First he is going to get to 1.94. 1.942. There is no nearly equal each other, you can say. And one more reading is 2.05, that is greater than 2, and 1.94 is 2 less, so 2.05 is 2 greater when compared to the true value. Therefore what I am going to say here is student B is not going to get the accuracy. He is not going to get the accuracy. Why? Because the particular values and the true values are not almost nearer to each other. Okay, and now we'll discuss about the precision. Okay, whether you are going to get the precise reading or not. Student B and the precision, I told you should not compare with the true value. So reading 1, reading 2. So 1.94 and 2.05, are these readings nearer to equal to each other? No, they are far away. Therefore what I am going to say is here there is no precision also. So the final statement what I am going to write is student B. Okay, the readings are neither precise nor accurate, neither precise nor accurate. So that is about the student B. So now the last one, you just think over it whether it is accurate or not, and what about the things we will see now. Student C, the first reading he is going to get 2.01 and second one will be 1.99, and first we will see what about the accuracy. So the true value is 2.0. Okay, and first reading he is going to get 2.01, 2.01, 2.00, almost near to each other. And second reading is 1.99 and 2.00, almost nearer to each other. So what I am going to say here is student C got the accuracy. So why you got the accuracy? Because when you compare the particular value and the true value, they are agreement or nearer equal to each other. Therefore student C, he is going to get the accuracy. And we will see what about the precision. Okay, precision means we are going to compare. Okay, 2.01 and 1.99, almost near to each other. Therefore that I can say he is going to get the precise reading also. So the student C, he is going to get both, the results are both accurate and precise. So this is how we are supposed to see whether the results obtained in the practicals, they are accurate or precise here, and this is a way how we are going to calculate that. I repeat, remember, accuracy is nothing but agreement of particular value to the true value. We are supposed to compare particular value and true value. If they are almost nearer to each other, accuracy. Okay, if not, we call it as no accuracy. Precision, closeness of various measurements for the same quantity. For the same quantity, the different readings what we get, if they are nearer to each other, and then we can say it as precise. If not, we are supposed to say not precise here. This is how we calculate what actually accuracy and precision. Practically, if you want to take any readings or any observations, okay, and you have to minimize the errors so that you are going to get a more accurate and more precise, so that the results will be almost nearer or exactly equal to the expected reading. Okay, so that is all about the concept called accuracy and precision. And now I am going to move with the next concept, that will be significant figures. Okay, so now we'll see what actually significant figure stands for, and what are the some rules and some examples we are going to discuss now. Okay, so the concept is significant figures. So try to know, significant figures are nothing but simple numbers. Okay, and they are simple numbers, they have particular meaning, we can say particular value, we can say. So meaningful numbers or meaningful digits with particular certainty, particular value, and that we call it as a significant figures here. Meaningful numbers with the certainty, we call it as significant figures. And if we want to calculate significant figures, we are supposed to follow some set of rules here. So here I made very simple set of rules, and if you know these rules, and one can get the significant figures for the given number. Okay, and in the examination, usually 1 mark question you are going to get, they will give one particular number and they ask you to write how many significant figures are there. So try to know significant figure means that is the number which has particular meaning, we call it as certainty, and that we call it as significant figures here. So we'll discuss one by one what are the rules, and examples also I have written, and I will tell you how to calculate the significant figures. Okay, so we'll move with the first rule. The first rule what we have here is all non-zero digits are significant. Significant, it has a meaning with a certainty, we call it as significant. All non-zero digits are significant. Non-zero, other than 0, from 1 to 9. Okay, non-zero, they are significant, he is going to say. Okay, so all non-zero digits are significant. We'll see the example. Okay, so the example I have considered here is 285. Okay, so now we'll see how many number of significant figures are there in a 285. So according to the first rule, what it says, all non-zero, 2, 8, 5. All the three are the number between 1 to 9, or can say they are non-zeros. And if we have a non-zero digits and all the digits are significant here, therefore the number of significant figures in 285 is 3. See here, 285 is 3. Why the significant figure is 3? Because 285, all the three are non-zero digits only. Right? One more example I considered here, 0.25. Okay, so 0.25, and you need to look over only non-zero digits only. Okay, so how many non-zero we have? 2 is non-zero, 5 is non-zero. Therefore, significant figure for this number is 2, because 0 we have, you should not consider, because 0 is not significant according to rule number 1. Therefore, in 0.25, the number of significant figure will be 2 here. Okay, so this is how, using the first rule, one can calculate the significant figure. So what the first rule says, in simple, you just try to know non-zero digits if you have, and all non-zero digits are significant only. And this is an example, what I considered. So now, after knowing the first rule, we'll move with the second one. So what is the second rule? Zeros preceding to first non-zero. Okay, so here zeros preceding to first non-zero, previous one, left side one, you can say. The zeros preceding to first non-zero digit are not significant. They don't have meaning. They don't have value. It is the meaning. Okay, I repeat, zeros preceding to first non-zero digit are not significant. So if you won't understand if you read only the statement. So now I will come to this example. So the example what I considered is 0.03. Okay, so first in this example 0.03, you consider which is the first non-zero. Okay, so the first non-zero is 3. Okay, so zeros preceding to first non-zero. So this is the 0 preceding to 3, and this is also the 0 preceding to 3. So these zeros are not significant. This is according to the rule. I repeat, the zeros, this is the first non-zero, and the number of zeros preceding to that is not significant. Therefore, how many significant figures are there? And according to the rule, these two are not significant. We have only 1, 3, and therefore the number of significant figures will be 1. I hope you got this one. If you didn't get, look into the one more example. One more example is 0.0052. Okay, and what you should first see, you should see the first non-zero. Which is the first non-zero? 5 is the first non-zero, and the zeros preceding to that, the 0 previous to that, the zeros left side of that, all they are not significant. Then how many numbers we are left? 1 and 2. Therefore the significant figure for this number is 2. Okay, so that is how I can give the example for the second rule. Okay, so second rule, you just try to know. In second rule, identify the first non-zero and the number of zeros, how many number of zeros we have left side of that or preceding to that, and they are not significant. Means you should not consider that. Okay, and you need to consider the remaining, and based on that you should write how many significant figures are there. Okay, so now we'll see the third one. And the third one is zeros between two non-zero digits are significant. Okay, it is quite simple. So if you have two non-zeros, okay, and if you have a 0 in between that, and that 0 is significant here, so in all the cases you should not leave 0. Some other cases you need to consider that here. In this particular example, if you have a 0 between two non-zero and that is significant here, so now example, you can understand this one, 2.005. Of course we have 0, but these zeros are in between two non-zeros, and if the zeros are in between two non-zeros, and these two zeros you need to consider, because these two zeros are significant. Therefore the number of significant figures we are going to get, what is that? 4. Is that okay? So you should know about that one. Okay, and if you have a 0, and if that 0 is in between two non-zero, you need to consider that as a significant figure. Okay, we'll see the next one, the fourth one. Zeros at the end of a number, see here, the zeros at the end of a number are significant, provided by, we have a condition here, provided by they are on the right side of decimal point, they are on the right side of decimal point. Here we are going to consider again 0, and this 0 is not preceding or not in between, and here we are considering 0 in the right part or end of the number here. So 0 at the end of a number are significant, okay, and if we have a 0 at the end of a number, that is significant only if we have a decimal point. Okay, if we have only the point, then that is significant. If you don't have decimal point and the 0 which is present at the right corner or end of the number, that is not significant here. We'll see the example. Here 0.200, okay, so 0.200, and now we'll see how many significant figures are there, and now you see whether this 0 is significant or not. The 0 point, this 0 is significant figure or not, and I hope we can guess this is not a significant figure. Why? Follow the rule number 2. The 0 preceding to non-zero is not significant, therefore this 0 you should not consider. And of course 2 is the non-zero we are going to consider, and we have 2 more zeros on the right side. So if we have zeros on the right side or the last digit of the number, then that is significant. When you have decimal point, we have here decimal point 0, isn't it? So therefore these zeros you should consider, whereas this 0 you should not consider, and the total number of significant figures will be 3, and you should not consider 0. This is 2 which is non-zero, and these 2 zeros you need to consider since we have a decimal point, and that is the right side of the number. Therefore 1 2 3 total, the significant figure will be 3, right? Now we'll say what about the significant figure in case of 100. Remember, just by seeing the number, don't try to attempt how many significant figures are there. Just you need to think over the rules what I told. Okay, so now 1 we have, that is non-zero, of course that is a significant figure. Okay, and if left side we have 0, and that is not significant, we know according to the rule number 2, but we have right side 0. Okay, so read the rule number 4 in very careful manner. The right side zeros are significant if we have only decimal point, but in this case we don't have decimal point, therefore the zeros which are present on the end of the number, the right side of the number, they are not significant here. Therefore the number of significant figure will be 1. Why 1? Because 1 is significant. These zeros are not significant even though they are present in the right hand side because of absence of decimal point. Okay, one more example. 100 point. Okay, 100 point. How many significant figures are there? We have 1, and we have these 2 zeros, and the total number of significant figure is 3 here. Okay, since we have a decimal point, but these zeros are left side here, there is no problem in that one. Therefore the number of significant figure is 3. And now look over the one more example, 100.0. So 1 is significant figure, these 2 are significant figure, and what about this 0, whether it is significant or not? Yes. Why? Because we have a decimal point, therefore the number of significant figures are 4 here. If you know the rule, then only you are supposed to get the significant figures. Okay, so rules are very important here. So try to know in rule number 4, the zeros which are present on the right side or the last side of the number, then that is significant if you have a decimal point, and if you don't have a decimal point, the zeros you should not consider. Okay, and now I am going to move with the 5th one. And what is the 5th one? In scientific notation. I hope you remember scientific notation is nothing but if you write any number in the form of capital N into 10 raised to n, that we call it as scientific notation. I explained this in the previous session. Two large number and two small number can be written in the form of n into 10 raised to n, and if you represent that form and that form of representing the number, we call it as scientific notation. Now here see, in scientific notation all digits are significant. So now if you observe this 4.01 into 10 raised to 10 raised to 2, and this is of the form n into 10 raised to n, and one can say this is scientific notation. And what the rule says, all the digits, okay, you need to skip this the exponential form, all the digits are significant. So 1 2 3, therefore the number of significant figures are 3. So now you come to this example, that is 8.256 into 10 raised to minus 3, that is in the scientific notation. Scientific notation, all digits are significant, 1 2 3 4. So then what actually the significant figures is 4. Now using this rule number 5, I am going to explain the previous one again. And now the question is again, why in case of 100 we have only one significant figure. See here, 100 I have, isn't it? I can write this 100, okay, I can write this 100 in this form, 1 into 10 raised to 2, isn't it? So this is the scientific notation. If you write 1 into 10 raised to 2, that is as good as 100. And in scientific notation all the digits are significant. So how many digits we have? 1. Therefore the significant figure of 100 is 1, and here 100 I have written 1. Okay, so using the next rule I have explained why 100 has a significant figure 1. So try to know, in significant figures all digits are, in scientific notation, all digits are significant. We'll see the last one. Counting the number of objects. If you have an object and they are countable, counting the numbers of objects have infinite significant figures. So here we have objects and you are supposed to count that, and if you have a counting objects, and how many significant figures are there? Infinite significant figures. Example, 2 balls. Ball is the object, and how many balls are there? 2 are there. So this is the counting object. Okay, so counting object has how many significant figures? Infinity. If I have given only 2, not object, only the number 2, you would have said the significant figure is 1, but this is not 2 alone. 2 balls we have, object we have, therefore the number of significant will be infinity. One more example, 20 eggs I have written. So 20 eggs are the objects, okay, and how many are there? 20, we can count that. Therefore this also has what actually the significant figures, infinite significant figures we have, and all these are the rules to calculate significant figures. Okay, so if you just read once, it will be a bit confusing here, and know that one in the examination, if you have a number and if they ask how many significant figures are there, you need to recall all the rules, okay, and you need to apply all the rules, and then you are supposed to calculate how many significant figures are there. Okay, so let me repeat that the rule in very simple manner. All non-zero digits are significant only, right? And if we have zeros preceding to the first non-zero, and these zeros are not significant, and if you have a 0 and that 0 is in between 2 non-zeros, and that is significant. And if we have a zeros and these zeros are the right or end of the number, and that is significant if we have a decimal point. And if you don't have a decimal point, even though the zeros we have in the right side, they are not significant. In a scientific notation, all the digits are significant. And the last one is, if you have a counting the number of objects and the number of significant figures, what you are going to get, that is infinity, right? And you need to solve some other problem so that you are going to get perfect in the calculation of significant figures. After knowing the concept of significant figures, I am going to discuss how to round off the numbers. Here I have very simple 3 set of rules, and using that we are going to round off the numbers. And here you need to consider the last or rightmost digit. You just see, if the rightmost digit is to be removed, we are going to remove the last number, rightmost digit, and you need to see whether the last number is more than 5. if the last digit is more than 5, the preceding number is increased by 1. In simple language, I can say, I am going to remove the last number and see the last number, and if the last number is greater than 5, more than 5, then the preceding number what you have to increase that number by 1. Example, see here, 1.386. So what is the last number? The last digit is the 6, and 6 is greater than 5. And if the 6 is greater than 5, what you are supposed to do? The preceding number what we have to increase it by 1. The preceding number 8, and 8 is increased by 1, that becomes 9. Therefore 1.39 you are going to get. So what we did, we just rounded off this number, that is 1.386 to 1.39 here, and try to know in 1.386, do you know how many significant figures are there? 4 significant figures are there. In 1.39, 3 significant figures are there. Sometimes in the examination they ask in the sense that you have to round up so that you are going to get 3 significant figures, 2 significant figures, like that, and in that case you need to consider which number should be the last thing you are supposed to see. Okay, so now that is about if the last number is more than 5. So now we'll see, let us assume the last number is less than 5. What you have to do? So if the last number is less than 5, see the rule, the rightmost digit to be removed is less than 5. The preceding number is not changed. The preceding number you have to keep as it is. You should not increase or decrease that one. So see the example, 4.334, and I am going to remove the last number, that is 4, and 4 is less than 5. So since 4 is less than 5, the preceding number what we have 3, and I am not supposed to change that. Therefore the rounding of this will be 4.33 you are going to get. Okay, that's it. In simple language I can say, if the last number is greater than 5, preceding number increase by 1. If last number is less than 5, preceding number keep as it is. And then the question arises, what happens if we have a number and the last number is exactly 5? Okay, see here, in such case, that is, if the last number what you are going to remove is exactly 5, then what is the case here? So look over here, if the rightmost digit to be removed is exactly 5, and then we have 2 conditions, then the preceding number is, you have to see the preceding number, and the preceding number not changed if it is even, and if it is increased by 1 if it is odd here. In simple language I can say, if the last number is 5 and you have to see the preceding number, if it is even, keep as it is, if it is odd, increased by 1. See the example. Here what we have, 6.35, the last number is 5. Okay, and see the preceding number you have to see whether it is even or odd. 3 is odd number, so what the rule says, if we have the preceding number odd, you have to increase by 1. Therefore what is the rounding off? 6.4 I am supposed to write. So one more example, we have the last number 5, the preceding number you have to see, and the preceding number is even. If the preceding number is even, then you should keep as it is, there is no change in that one, therefore that is 6.2. So this is how, using the concept of significant figures, and we are supposed to round off the given number according to required significant figures. So here I just eliminated the last number, and these are all the rules how to eliminate the last number, and that's we call it as rounding of the number. If the last number is greater than 5, the preceding number has to be increased by 1. If the last number is less than 5, the preceding number remains as it is. If the last number is exactly 5, see whether the preceding number is even or odd. If it is even, keep as it is. If it is odd, increased by 1. This is in very simple way how I can explain rounding of the numbers. After rounding of the numbers, we'll see dimensional analysis. You can call it as a unit factor method or factor level method. Different ways of naming we have. Dimensional analysis. So what actually we are going to use this one? Of course, in some cases we need to solve the problems, and while solving problems we consider the particular problems with the given data in one set of units. Okay, and in that cases we are supposed to change the units here. Okay, and that kind of changing the values according to the units and that kind of method while solving the problems, we call it as dimensional analysis. The method used to convert a unit from one system to another system. If you are converting Kelvin to degree Celsius or any one system to another system while solving problems, that procedure or method we call it as dimensional analysis, and that is going to be helped while solving problems here. We have n number of problems and I consider very simple problems, and here I am going to explain how dimensional analysis is going to be used. Remember, in this particular example what I consider, I am not going to explain how to simplify or how to solve the problem. Here I am going to explain how unit factor method or factor level method or dimensional analysis is going to be used to solve the problems here. The problem is, a piece of metal is 3 inch long. 3 inch long I have a piece of metal, and what is its length in centimeter? So now see, we are converting inch into centimeter. We are converting the unit from one system to another system and using the dimensional analysis here. I told you already, here the solving is not important one. How to use a unit factor is the important thing here. So what I am going to write here is, so I am going to explain here. So 1 inch, we know that 1 inch is equals to 2.54 centimeter. You need to know 1 inch is equals to 2.54 centimeter. This we know that one. Okay, so we know that relation. 1 inch is equals to 2.54 centimeter. Okay, and what I am going to do is, from equivalence, I will tell you what is that actually. From equivalence and unit factor method, I am going to write one relation. Just to see what is the relation I am going to write here. So 1 inch I am going to write here divided by 2.54 centimeter, which is equals to 1, which is equals to 2.54 centimeter divided by 1 inch. So this we call it as the unit factor representation. So what is the actual meaning of that one? Why we call it as equivalence here? 1 inch divided by 2.54 centimeter. The same thing I have written in the form of ratio. Okay, and if you take the inverse of that one, exactly opposite, and these two it cancels, you are going to left with one number, the same number. Okay, and that's why I use the word equivalence, means these two are the same. Okay, so since this we call it as a unit factor, you try to know this is one unit factor and this is one more unit factor. So in this equivalence I have two unit factors. One is this one, 1 inch by 2.54 centimeter. One more unit factor is 2.54 centimeter divided by 1 inch. I am going to use this unit factor. So what is the advantage of using the unit factor? Know that one. If you consider any unit factor and if you multiply it by any number, the unit factor remains same. I repeat, if you consider the unit factor and if you multiply the any unit factor by any number and the value of the unit factor remains same. Why? Because if you consider unit factor and the value will be always 1, and that we call it as, what is that? Equivalence. So either of two you are supposed to use while solving the problems here. So try to know, I am going to convert inch into centimeter. Okay, so what is the given inch I have here? So I have 3 inch long. Okay, so 3 inch long the metal, I am going to convert into centimeter by using this factor method. Okay, so 3 inch I am going to write here. The same thing I am going to repeat, 3 inch. We are going to simplify 3 inch into centimeter. You need to consider 3 inch into, and you have to multiply the unit factor. Okay, I told you this is the one unit factor and this is the one unit factor. The question is this, out of these two, which one is going to be used? And that depends on in what way, how you are converting the units. I am going to convert inch into centimeter. So therefore, I am going to use this one. Okay, why? Into, I am going to write here 2.54 centimeter divided by 1 inch. I told you already, inch is going to be converted to centimeter. I am going to use centimeter because the last I need the answer in terms of centimeter. If I need the answer of in inch, I would have taken this as the unit factor here. Okay, so now I am going to simplify that one, and in simple method I can say this inch get cancels here, and what you are left with 3 into 2.54 centimeter, and if you multiply that, I hope you are getting approximately 7.62 centimeter you are going to get. And what is this actually? This is 3 inch. So this is the way how we converted 3 inch into centimeter by using the unit factor method. I told you that already, the unit factor what we have, and if you multiply that with any number, the value remains as it is. Therefore, this unit factor is multiplied by 3 inch. There is no chance of varying the values, because that is unit factor. And if you have a unit factor, multiply with any number, the value won't change here. Okay, so here you would have directly converted by using this relation from inch to centimeter. Here I told you that I am going to explain here the method or unit factor method here. Okay, this is how unit factor method can be used here. Okay, so that depends, 2 unit factors out of these 2 which you are supposed to use, that depends on the conversion how you are supposed to consider. This is one very simple example how I explained by converting inch into length, and similarly you can convert liters into meter cube, you can convert days into seconds. Okay, so different units what we have, we can convert that. But remember, if the question is using a dimensional analysis or unit factor method, you are supposed to use unit factor like this, and you should know how to write the unit factor. And writing the unit factor depends on the relationship between the given quantities. So the relationship between inch and centimeter you should know. Similarly, the relationship between the seconds and minutes, the liters and cm3, you should know about that one, and using that relation one can guess the unit factor, and out of 2 the which one you need and you are supposed to consider, and you are going to get the sorts of problems, the correct answer you are going to get. And here I converted the unit from one system to another system, and that we call it as a dimensional analysis. Now we'll see the laws of chemical combinations. Totally we have 5 different laws of chemical combination. Law of conservation of mass, law of definite proportion or composition, law of multiple proportions, Gay-Lussac's law, Avogadro's law. So totally 5 different laws of chemical combinations we have. We'll discuss one by one. We know that one, elements combine, you are going to get a compound, and this is how the combination takes place. And the combination of elements to form a compound depends on the 5 different laws what we are going to study now. We'll see the first one. The first one is law of conservation of mass. As the name indicates, mass is going to be preserved or conserved. So what is the statement given by? Matter can neither be created nor be destroyed. In simple sense, I can say you cannot create matter or you cannot destroy matter also. So that is a statement of law of conservation of mass. We'll understand this better by considering the example. So now I am going to consider one simple example, that is when carbon is burnt in the presence of oxygen, we are going to get a carbon dioxide. So this is one very simple combination reaction. Carbon undergoes oxidation, you are going to get a carbon dioxide. So now we will see how matter is not created or not destroyed, we are going to see. And it is the same case in case of all kind of reactions what we see. So for that one, first we will see about the matter is nothing but we are talking about the mass, isn't it? Because matter has a particular mass. So we will see what about the masses of carbon, oxygen and carbon dioxide. And we know that one, the each element has atomic number and atomic mass. Okay, and the molecular mass is nothing but the sum of atomic masses of an element, we call it as a molecular mass. You know this well. So now carbon Okay, so carbon atomic number is 6 and atomic mass will be 12. Let us assume 12 grams of carbon we have here. So now we'll see that is nothing but oxygen. So oxygen, how many oxygens we have? We have 2 oxygens. Okay, atomic number of oxygen is 8 and atomic mass will be 16. Okay, so 2 into 16 grams we have. So now we'll calculate the amount of matter or mass before the reaction. Okay, so 16 into 2, 32 we have, and 32 plus 12 grams, and totally we are going to get what? Actually 44 grams. So what is the meaning of that is, before the reaction the total mass of carbon and oxygen is 44 grams. Okay, and that will react and you are going to get a new product, carbon dioxide. So now we will calculate what about the mass of carbon dioxide here. So carbon we have one atomic mass will be 12. Okay, plus oxygen, and how many oxygens are there? 2 are there, and 1 oxygen, that will be 16 atomic mass. 16 into 2, 32 plus 12, we are going to get what? Actually 44 grams here. So one can easily guess that before the reaction the mass is 44 grams, after the reaction the mass is 44 grams only. The mass has not been changed. Of course there is a chemical change has been occurred here. Okay, by considering this very simple example, you can consider n number of reactions, and if you calculate the mass in the reactants and in the products, that will be always equal, and that we call it as what? Actually the law of conservation of mass. And the statement is, matter can neither be created nor be destroyed. But remember, in some cases what happens, there will be change in states of matter only. That's about the first law of chemical combination, that will be law of conservation of mass. The second one we'll see, that is law of definite proportion. You can call it as law of definite composition also. Let me read the statement. A given compound always contains exactly proportion of element by weight. We know that one compound is formed by elements only. Okay, and that elements in terms of weight, they had exact proportion or exact composition. So that is the meaning of the law of definite proportion. So now I will consider example, then you are going to understand it better. So now the example what I am going to consider is, I will consider one compound, very simple compound, water. H2 is a compound. Okay, and now in water we have 2 different elements. What are those? One is hydrogen and one is oxygen. Okay, we know that one water is a compound. In water we have 2 different elements, hydrogen and oxygen, and I can write like this by chemical equation. Okay, so now what we are going to say is, what is the proportion of elements? That is nothing but what is the proportion of hydrogen and oxygen in water we are going to see, and according to the rule, that is a fixed composition or the ratio we have. Okay, and H2 plus O2, and here I am going to write what? Actually half O2, that is nothing but to balance the correct equation. So now we are going to see what about the composition of elements in this particular compound. Remember, we are talking elements by weight itself here. So again the molecular mass and atomic mass I am going to calculate, and here one can easily guess, hydrogen, the atomic mass will be 1, and we have 2 hydrogens, 2 into 1 I can write, plus oxygen, atomic number is 8, atomic mass is 16, totally water it has 18 grams I can write. Okay, and hydrogen atomic mass is 1, we have 2 hydrogens, so here I can write 2 grams, right? And we have half already, and 2 oxygens are there, and each oxygen atomic mass is 16. 2 to get cancels, we are going to get what is that? 16 grams. So what is the meaning here? I have written in this reaction is, 18 grams of water contains 2 grams of hydrogen and 16 grams of oxygen. I repeat, 18 grams of water has 2 grams of hydrogen and 6 grams of oxygen. And if you consider the ratio of hydrogen and oxygen, let me write that. Okay, so here I am going to write what actually the ratio. Okay, ratio of hydrogen and oxygen. What is the ratio of hydrogen oxygen? 2:16. Okay, or you can write what actually 1:8. So 1:8 is the ratio or the fixed proportion what we are going to see in case of water. Practically, what is the meaning is, if you consider water from any source, it may be river water, rain water, ocean water. If you consider a water, one condition is that should be pure water, okay, and that has hydrogen and oxygen elements in the ratio 1:8. That is fixed. Okay, one more in the one more way I can say, if you consider a compound, what is that? Water, and the compound has elements, that is hydrogen and oxygen, and these elements are in exact proportion by weight. Okay, and that we call it as law of definite proportion. And I think now you are going to get what is the actual meaning. A given compound always contains exactly proportion of elements by weight. By weight is the condition. By weight it has the exact proportion, and this is a very simple example what I am going to give here. That is about the second one, that is law of definite proportion. The third one we'll see. The third one is law of multiple proportions. Multiple proportions. We'll see the statement first. If two elements can combine to form more than one compound. In the previous one, two elements combined and you got only one compound. In this multiple proportions, two elements are going to join and you are going to get more than one compound. See what we have then. The masses of the one element that combined with the fixed masses of the other element are in the simple ratio. That will be in the small whole number, and that is the statement of law of multiple proportion. I will give you example, then you are going to get the understand from that. When hydrogen combines with oxygen, and I hope you guess you are going to get the product, that will be H2O. Hydrogen combines with oxygen, you are going to get H2O. Remember, if you consider the same, that is when hydrogen combines with oxygen, we have chances of formation of hydrogen peroxide. Know that H2O2 stands for hydrogen peroxide. If we pass excess amount of oxygen, peroxide, extra oxygen you are going to get. Therefore H2O is water and H2O2 is a peroxide. Okay, and for the balancing, for the first one I am going to write what actually half O2. So try to know H2O2, the two elements we have. Here also H2O2 we have two elements, but how many compounds we get? More than one compounds, isn't it? See here, if two elements can combine to form more than one compound. Okay, that is the example what I can give. Further we'll see the masses of one element that combined with the fixed masses of the other element. We need to see the mass, isn't it? So what is the mass of hydrogen? Now I hope you can easily guess. What is the mass? 2 grams. Okay, and what is the mass of this oxygen? That will be 16 grams, 1/2 O2. Okay, 16 grams. So now we'll see here in case of hydrogen it is 2 grams. Okay, and here it is 32 grams O2. One oxygen is 16 and 2 into 16 we have 32 grams here. Okay, so now we'll see the masses of one element that combines with the fixed mass of the other element. So now out of these two, that is hydrogen and oxygen, we have to see which is the element which has the fixed mass, and that is the hydrogen. So in this case the mass of hydrogen is 2 grams, and in this case also the mass of the hydrogen is 2 grams. The oxygen is going to be varied, and if you take the ratio of that, that will be in the form of simple whole number ratio. So now what is the ratio of oxygen? I will write here the ratio of oxygen. What is that? 16:32. See here, 16 grams and 32, or you can say 1:2. So that ratio also we can write, and that will be always in simple whole number ratio. Okay, so that is the best example what I can give. So try to know that one. If two elements can combine and you are going to get more than one compound, then the masses of one element that is going to be combined with one more element which has the fixed mass, and then the ratio of the mass that is going to change, that will be in a very simple ratio, and that we call it as the law of multiple proportions. I repeat, If two elements can combine to form more than one compound, the masses of one element that is combined with the fixed mass of the other element are in the ratio of a small whole number. In this case of the formation of water and hydrogen peroxide, the ratio of oxygen here and here, that will be 1:2. I am going to say. We'll see the fourth one, Gay-Lussac's law. Remember, Gay-Lussac's law is going to be applicable for gases. And here we are going to talk about the volume here. Okay, so what is the statement? First we'll see, when gases combine or produced, when the gases combines or when the gases are produced in a chemical reaction, they do so in simple ratio by volume at the same temperature and pressure. So what is the simple meaning? The temperature of particular gas will be fixed, temperature and pressure, and the gases may combine and the gases may produced. Okay, but the volume what we are going to get, and that will be in the very simple ratio. The volume combination or production will be the simple ratio. We'll see example, then you are going to get understand. Otherwise it will be very difficult. Without example it is difficult to understand. Hydrogen is gas we know, and chlorine is gas we know, and we are going to get the gas, we call it as hydrogen chloride. Hydrogen chloride, hydrogen gas, chlorine gas, HCl, hydrogen chloride gas. If it is dissolved in water, we call it as hydrochloric acid. For balancing, I am going to write a 2 here. Remember, this reaction takes place in bright sunlight. In a dark place, the reaction won't take place. Let us assume this reaction takes place in bright sunlight, and this is the two gases are going to combine. Okay, so now I told you already, if we have a gases, and that is going to be related to Gay-Lussac's law, and Gay-Lussac's law we are going to talk about a volume only. Let us assume, what is that, 100 ml of what hydrogen we have, that combines with the 100 ml of chlorine, and we are going to get what actually 200 ml of HCl. So in terms of volume, milliliters. Okay, and what happens here, that will be in simple ratio. So what is the ratio I am going to write here? The ratio of volumes of these three gases, hydrogen, chlorine and hydrogen chloride, the ratio will be 1:1:2. I can write like this, isn't it? 100, 100, 200, 1:1:2. So if you consider the formation of hydrogen chloride, the ratio will be always 1:1:2 only. So this is the reason when the gases combine or produced in a chemical reaction, they are supposed to get so that their volume should be in terms of a simple ratio, and provided the temperature and pressure is going to be kept constant, and that is the law, we call it as Gay-Lussac's law. Last one, Avogadro's law. Statement will see, equal volumes of all gases at same temperature and pressure contains equal number of molecules. So try to know, equal volumes of all gases contains equal number of molecules. Very simple here. Equal volume we have, the number of molecules should be equal. We'll see example, then you will understand. The same compound I am going to consider, H2 and Cl2 reacts in the presence of sunlight. We are going to get what is that? 2HCl. Okay, and I hope we can guess that follows the Gay-Lussac's law, because all the gases, okay, and one volume and two volume. If you consider in terms of liters, okay, and you can consider any liter or milliliter, in general, one volume of hydrogen combines with one volume of chlorine, you are going to get what is that? Two molecules of HCl. So if these have equal volumes, then the number of molecules will be equal. Okay, so let us assume here we have one molecule. Okay, and if volume of these two are same, therefore this is also one molecule, and the volume of this when compared to this, and this is going to be doubled, therefore I am going to consider what is that? Two molecules here. So equal volumes of all gases has equal number of molecules provided the same temperature and pressure. Okay, so one more sense I can see here. Okay, so if we have a what actually 100, okay, 100 liters we have. Okay, so 100 liters we have, and let us assume n molecules we have here, n molecules, 100 liters of gas we have, and we have n molecules, and if I transfer into 50 liters, okay, so what would be the number of molecules? based on Avogadro's law, if the volume is reduced by half, then the number of molecules is also be reduced by half. Therefore, I am going to write n by 2. Why? Because equal volume if you have, then the number of molecules will be also equal, and that is about the last law, we call it as Avogadro's law. So all these laws, what are those? Law of conservation of mass, law of definite proportions, law of multiple proportions, and Gay-Lussac's law and Avogadro's law all together stands for law of chemical combination. And just by addition or something we cannot write the reaction, that has to follows all these laws here. That is about the very simple, the 5 different laws of chemical combination. In the next class we'll discuss about some other concepts of chemistry. Thanks for watching.